Okay, so our next speaker is Andrew Wetzel, who will talk about ISM of Milky Way mass galaxies in FIRE-2, metallicity variations, and GMCs. So please go ahead.
Okay, thank you. Yeah, so the general theme of my talk is the ISM across the histories of Milky Way mass galaxies in our FIRE-2 simulations. And I'll touch on two distinct but related topics, metallicity variations and the properties of giant molecular clouds in these simulations. And here's just a movie of the evolution of the ISM since Redshift 1 in one of these Milky Way mass simulations. So most results I'll show you is from our full current suite of Milky Way mass galaxies. So that's these are all cosmological, but 8 of them are relatively isolated, so individual Milky Way mass systems. And then 3 local group-like pairs, that gives us 6 halos. So we have a total of 14 Milky Way mass galaxies. Most of the results I'll show you are these simulations at mass resolutions of a few thousand solar masses. And again, just to reemphasize, everything I'm going to show you is across the histories of what are present-day Milky Way mass galaxies. So for those of you who think more at high redshift, the stellar masses of these galaxies is roughly 6 by 10 to the 10 today. If we go back to redshift 1, the typical stellar masses were about 10 to the 10 or 2 by 10 to the 10. And at redshift 2, for example, stellar masses of a few by 10 to the 9. So the first part of my talk, I'll discuss work by one of my PhD students, Matt Bellardini, looking at the 3D variations in metallicities, in elemental abundances, across the formation histories of these Milky Way mass galaxy simulations. And one of the motivations is, of course, the exquisite data we have today for the Milky Way, right? So surveys like Apogee have been mapping out local metallicity distributions of stars, and soon we'll have surveys like Sloan 5. They're going to map essentially the entire Milky Way. And so we'll have exquisite information, not just on dynamics, but also on elemental abundance patterns. And one of the guiding ideas is the idea of chemical tagging, where if we've measured elemental abundance patterns for stars of different ages across the Milky Way today, we should be able to use that to recover the full 3D formation history of the galaxy, what stars formed in what part of the galaxy and when. So that's a lofty goal. One of the things we have to understand if we're going to use chemical tagging is what were the initial conditions of metallicity variations in the Milky Way across its history when the stars formed, right? So we need to model metallicity of each element as a function of age, or look-back time, as a function of radial position in the galaxy, as a mutual position in the galaxy, and in principle, although in practice not necessarily very important, the height above the disk. And this is of tremendous interest for models of chemical tagging. But of course, for many of you also working on high redshift galaxies, you're able to measure directly the metallicities of the gas at high redshift. And so I think it's important that we get a consistent picture of what these metallicity variations look like in galaxy populations across time. All right, so here is the mean iron abundance as a function of age across all of our simulations. So this is the metal enrichment history of our Milky Way mass galaxies. It looks as you'd expect. Early on, the galaxy underwent rapid enrichment, and then of course over the last several giga-years there was continuous enrichment but at a sort of diminishing rate. And so often we sort of have in our minds that the metallicity or the iron abundance is a good proxy for the age of stars in a galaxy. But we need to be a little bit more careful because of course not all stars forming even at the same time have the same abundance. So one thing to think about is what would your expectations be for how much scatter there is in metallicity for all the stars forming at a single time in a galaxy as a function of its history? What would the shape of this history look like? Would it be highest today or highest in the past? The answer is both. So here's what we see. It has this interesting dip where metallicity variations were quite high at early times, and then they came down, reached a minimum about 7 to 8 gig years ago, and then came up again. And essentially what we find is this a competition between two processes, one of which is the declining importance of azimuthal variations in the galaxy, and that competes against the increasing importance of the onset of the radial gradient of the galaxy. And these lead to this sort of U-shaped dependence of the total metallicity variation in the gas at fixed time as a function of age. So to break that down a little bit more, so here's just a top-down image of one of our disks at redshift 0, color-coded by, in this case, the oxygen abundance. You can see a nice radial gradient. Of course, you can also see some azimuthal variations following spiral arms. It's quite interesting. I'll say more about that in a moment. But if you look back in time, you can see, especially once we get to redshift 1 or below, there's a less clearly evident radial gradient, although it's still there to some degree, but what we start to see is the onset of increased importance of azimuthal variations. So at redshift 0, radial gradients dominate in these Milky Way mass galaxies, but at earlier times, if we go sufficiently early, it's actually the azimuthal variations that are the dominant metallicity variations in these galaxies. So just as a quick benchmark of what the radial gradients look like at redshift 1 to show that we're forming disks that are in the right ballpark, here is the oxygen gradient, so dex per kpc, the radial gradient. The band shows the results from our simulations, so a typical gradient is something like minus 0.03. And then these boxes show different measurements of different surveys of nearby Milky Way-like galaxies. So you can see we're in the right ballpark compared to measurements of gas phase radial gradients in nearby galaxies. We can also compare it to measurements of M31. They're a little shallower than our simulations, but again, the right ballpark. The kind of interesting thing is if you put the Milky Way on this diagram, it's significantly steeper. So it does look like this is a sense in which the Milky Way is a bit of an outlier compared to a lot of galaxies in the local universe, which is that it has a somewhat steeper metallicity gradient either than our simulations or nearby systems. But my point is that the gradients today in these simulations are reasonably comparable to the Milky Way and nearby galaxies. So then we can look at what the radial gradients look like going back in time. So here's the average radial gradient today, right? You can see a nice negative gradient here going from the inner galaxy to the outer galaxy, and then going back in time, right? The key idea is that the radial gradient almost entirely goes away such that by 11.5 gigayear look back time, there is essentially no meaningful radial gradient anymore. And the rough picture is that the strength of this gradient is tracking the dynamics of gas in the disk. When V over sigma is high, the gas is on near circular orbits. The galaxy can maintain strong radial segregation of the abundances to maintain this gradient. But at high redshifts during turbulent disk formation, or before the onset of the disk settling, during the turbulent ISM phase, there's simply too much mixing, so this galaxy is unable to sustain a strong radial gradient. And so this just shows the strength of the gradient as a function of look-back time. Don't worry about the different lines, just look at the blue curve here, where the gradient is strongly negative today, but if you go back far enough, if you go back to about redshift 3, our Milky Way progenitors basically had no measurable gradient. It can occasionally scatter to positive, but typically it was 0 at these times. And so we can then compare the relative strength of the radial gradient to the azimuthal variations by just measuring the total difference in the abundance going from the R of 0, the center of the disk, out to the edge of the disk. This is the total change in this case, the iron abundance. And then the orange curve shows the change from R at 0 to R90. And by comparison, the blue curve shows the strength of the 360-degree azimuthal variations as you go around the disk. And again, the key is, of course, the radial gradients dominate today. The azimuthal variations are small but measurable, comparable to measurements of nearby galaxies, something like 0.05 dex. But if you go back before about redshift 1, it's the azimuthal variations that were actually the dominant variations, not the radial gradients. And just because it seems like a theme of this meeting is to show James Webb results, why not? So I'll just highlight just one version I thought was interesting, a recent paper. Tucker Jones, colleague of mine at UC Davis, had a hand in this. So glass JWST measurements with NIRISS of a galaxy that's actually roughly a progenitor mass of the Milky Way at redshift 3. And in this paper, if you read it, they sort of made a big deal that they're seeing hints of positive metallicity gradients in this galaxy, although to my eye, that looks not that inconsistent with just a flat gradient. But if you look at the raw metallicity map on the left, to what my eye sticks out, and I'm a little surprised they didn't emphasize it more, isn't any sort of radial gradient. It's these extremely strong azimuthal variations, in part driven by the clumpy star formation. So I think there, maybe if you, those of you looking at high redshift galaxies, maybe this is well known, but for the Milky Way community, I think is still digesting this idea that at early enough times, it was really the clumpy azimuthal variations that were dominating. And so when we think back to applications like for chemical, before I'll summarize, so just as a summary of what I just said, the overall metallicity over the course of time increases as you expect. The radial gradient steepens over time, but the azimuthal scatter reduces, and there's a competition between these. And so it's in our Milky Way simulations before about redshift 1, it's the azimuthal variations that are dominant. And I think there's a lot more work that needs to go into the Milky Way community of how to deal with these azimuthal variations, and if we can even model them at a level that allows us to use chemical tagging at this early time to understand where the stars were forming. So that's the end of the first part of my talk. I'd now like to move on to smaller scales and discuss the properties of giant molecular clouds in these simulations. Again, here's just a movie of the light distribution on the left and then the gas on the right. Give you a visual sense of what the dense and molecular-ish gas would look like in one of these simulations. And this is an interesting time to think about properties of molecular clouds and star clusters in the nearby universe, because surveys like FANGS are in the process of measuring some tens of thousands, I think up to 100,000 GMCs and star clusters in nearly 100 nearby galaxies. Here's one of their beautiful, recently released James Webb images of M74 here, and you can see the nice gas distributions and star-forming regions here, really exquisite data. And I couldn't help but show a comparison of one of their earlier images. So there's M74 on the left, there's one of ours on the right, right? Color scheme looks nice, it looks very similar, right? So clearly the simulations must be correct. Okay. Okay, more quantitatively, however, the first question I'd like to present is work by Samantha Benincasa, who was formerly a postdoc with me at Davis. She's now a postdoctoral fellow at OSU. And she started looking at the lifetimes of the molecular clouds in our simulations. This is at redshift 0 now. And so here's just a top-down image of the map of GMCs in one of these simulations. And here is the mass function. So this is number of clouds versus mass. She looked at 3 of our more Milky Way-like simulations. Here's the mass functions of GMCs compared to observations of the Milky Way and M51. And we can see we're getting mass functions that are in broad agreement with nearby cloud mass functions. We're resolving things from a few by 10 to the 5 up to a few by 10 to the 7 at redshift 0. So she looked at how long-lived clouds are in that mass range in our Milky Way mass simulations at redshift 0. And here's a histogram of the lifetimes. So and this is in all clouds that are essentially overdense molecular clouds. And so the peak of our cloud lifetime is something like 7 megayears. It falls off, and we don't find any clouds living longer than about 20 million years in these simulations. And here's just sort of an image of one case study of what's going on. So here you see at time 0 a cloud that's in the process of collapsing. 2 million years later, a star cluster is formed, and just 2 million years after that, before the onset of any supernova, because of the combined modeling of stellar winds, photoionization heating, and radiative pressure, these stars are already starting to evacuate and destroy the cloud that they formed in this one example. So these are the typical lifetimes across all of the simulations. We can also ask how do the cloud lifetimes vary with any interesting parameters within these galaxies? So the first thing we can look at is radial dependence within these galactic disks. We don't really find very strong radial dependence to the cloud lifetimes. They're maybe a little bit shorter in the bulge regions. We can also look at the dependence of lifetimes on the mass range. So at least within the mass range we can probe roughly a factor of 100 or a little bit less. We don't really see any evidence for mass-dependent lifetimes. The most important parameter by far is how self-gravitating the clouds are. So for very non-self-gravitating clouds, we're essentially capturing transient overdense molecular regions. They basically live a dynamical time. They have no choice before they disperse. It's only when we look at our self-gravitating clouds, here we start to see sort of the classical picture, which I just showed you before, cloud lifetimes here extending to more like 10 million years. So it's the self-gravitating clouds that actually form stars that go through this full cycle. And we can compare these with observational inferences of cloud lifetimes from surveys like FANGS. So for example, Dietrich Huyssen has done some nice work in this area. The idea is you can make these tuning fork-like diagrams where you center your regions on either dense molecular gas peaks or on star-forming peaks, and you start to see that on sufficiently small scales they become dissociated. And you can use this to model sort of this time series where you have a gas cloud collapsing. There's some overlap region during star formation before the feedback from the stars dissociates the cloud, right? And if you look at the work that, for instance, Dietrich and his group have done, they're finding implied cloud lifetimes in FANGS that are something like 10 to 20 million years, in general agreement with what we're finding in FIRE. And there's actually quite a lot of work in this area, to my knowledge, all of which, at least at redshift 0, are finding cloud lifetimes that are essentially in this ballpark. So there seems to be general agreement that at redshift 0, cloud lifetimes are of the order of 10 million years. Okay, so that's at redshift 0. So now, a different investigation led by David Guzanov, who I think is about to start as a postdoctoral fellow at Harvard. David looked at whether the properties of clouds in these simulations are varying across their histories. So we can look at, for example, a map of clouds in one of these Milky Ways today, And we can go back to redshift 2 and look at the properties of clouds back then. So how similar or different are the populations of clouds across the formation histories of a Milky Way mass galaxy? So the first thing we can look at is the mass functions of the clouds. So here's number of clouds versus their mass. And the somewhat surprising thing, at least I was somewhat surprised, is how little variation we see in the mass function of clouds across these histories. So these are just 3 randomly chosen snapshots, 1 gig year ago, 7 gig years ago, and very early in the history. Sorry, this is the age. So this is today, and this is going back in time. And we can see some minor changes, but for the most part, these mass functions are looking similar. Yes, of course, you can find rare events of mergers where you have a temporary enhancement of the mass event of the mass function. But if you just time sample the snapshots in these simulations, for the most part, the mass functions are looking relatively self-similar. So we don't see huge variations, typical snapshots of the mass functions of these clouds. We can also look at the internal properties of these clouds. So this is just plotting the mass size relation and the velocity dispersion size relation. And these dotted curves show comparisons to Larson-like scaling relations, just to show that these clouds are sort of in the right ballpark as far as the observed scaling relations of clouds in the Milky Way for comparison. So David also looked at how the internal properties of the clouds or whether the internal properties of the clouds are varying. So here's the time evolution of the internal velocity dispersions, time evolution of the sizes, time evolution of the surface densities of these clouds. And we see very little systematic evolution in the properties of these clouds across Milky Way histories. I must have said something profound. The only thing we did see modest evolution is because, of course, these galaxies are metal enriching over time. The clouds were necessarily more metal poor at early times, so that affects their cooling, right? So if you go back earlier, so relative to today, earlier on, there was a relatively less efficient cooling, and so the ratio of turbulent to thermal energy was going down as you look back. So earlier in the formation history, because of the reduced cooling, the thermal pressure was slightly more substantial than it is today. That's the one thing that we saw systematic evolution for. All right, so that's the end of my talk, but before I leave, I just want to advertise that as of February, all of the FIRE simulations are now publicly available to download and be used. We've released essentially all of our different mass simulations from Milky Way down to ultrafaint at a variety of different, actually we've also had some massive FIRE simulations as well, and some epoch of ionization simulations, and we've released multiple snapshots per simulation. So if you're interested, you can just have a look here. So that's the end of my talk. So just to recap, we looked at the evolution of the spatial variations in metallicity, finding that at early times azimuthal variations dominated. Today, however, radial gradients dominate. We find cloud lifetimes at redshift 0 that are of the order of 10 million years, and we find strikingly little evolution of cloud properties across the histories of these Milky Ways. Thanks.
Right, thanks, Andrew. Questions? Let's start with Frank.
2 quick questions. Very nice talk. The first part of your talk, the gas metallicity, you argued that the lack of a radial gradient at high redshift is plausibly explained due to the fact that the disk is very turbulent and causing a lot of turbulent mixing. Why shouldn't that then also erase the strong azimuthal variations that you see?
Well, it does over time, but I think the key is that the star formation itself is highly clumpy, so the initial injection may be inhomogeneous, but then they're those abundances will mix very quickly on a dynamical time. So I think the point is that star formation is, right, so you can have momentary periods of maybe radial variations, but those will mix away very quickly. The azimuthal variations will also mix away, but this is just showing you what you're getting at sort of a fixed moment in time. If you look at the resultant stellar populations, they'll mix very quickly after they form.
And then the key question was, I was hoping you were going to answer that when you started talk. Is chemical tagging going to work, yes or no, based on your insights gained?
Yeah, so if I was giving a longer talk, I'd have more to say on that. I think, so to elaborate a bit, there's sort of 2 different flavors of chemical tagging people talk about, sort of strong chemical tagging of recovering individual star clusters that may have formed. And there's a weaker form of chemical tagging, which is really just how did the disk form? I think the disk-wide stuff is still very viable. I think the individual star cluster chemical tagging is viable for relatively young star clusters whose stars may still be phase coherent today. I think doing anything beyond that for stellar populations that are older than 6, 7, 8 gig years ago is going to be very, very challenging. You might still be able to disambiguate in situ versus ex situ stars, but if you're just talking about in situ, I'm not very pessimistic about modeling that regime. Sorry, I'm not very optimistic. I am pessimistic.
So you mentioned that at redshift higher than 1-ish, there's the azimuthal gradient dominates, right? I wonder if that's simply because galaxies are just irregular and just not axisymmetric, or there's some...
That's part of it. Star
okay.
formation is not axisymmetric for sure.
Could it be related to that the filamentary accretion, so you're actually sampling as you go from different degrees, right? So in the filament, out of the filament, in the disk.
I think that probably plays a role, yeah. I mean, we didn't look at that in any more detail.
So I'm going to ask you the question that we've asked before about the mass of the stellar clumps. As various people have already shown, we see stellar clumps in a majority of star-forming galaxies at redshifts greater than 1, with masses greater than 10 to the 7, going up to 10 to the 9. Your giant molecular clouds seem to peak out at about 10 to the 7, even at high redshift. And you didn't talk about the masses of the stellar clumps, but since a majority of galaxies that will turn into Milky Ways are clumpy, with fairly massive clumps, at least as far as we can tell, is that consistent with your simulations?
I think that's something we need to look at more carefully. I don't have a deep answer for you right now because we haven't looked at it specifically. I can say, for the sake of time, I didn't know, we're starting to quantify the star cluster populations in these simulations and star clump populations. We do see star clusters up to mass, today star clusters as massive as 10 to the 6 or so forming. We're in the process of looking at this at high redshift, so I can get back to you. I don't have a very quantitative answer for you right now.
Andrew, high-resolution images of the ISM indicate that many GMCs are nothing like what we thought they are. I mean, not round, nice things, but rather filamentary. There's a wonderful picture of the Orion Nebula filamented zone. So my question is your simulation recover anything of this sort?
Yeah, we didn't look at the morphologies of the clouds, but I mean, if you sort of do a by-eye morphological decomposition here, I wouldn't say we're seeing very clean spherical clouds here. I think we're seeing highly triaxial over dense regions. But we haven't quantified that carefully yet. That's something we should do.
We still have time for a few more questions.
Thank you very much. No mentions made of the thickness of the disks. I'm curious whether among your Milky Way candidates or models, how much variation is there in the thick disk? And does the thickness of the disk affect at all the GMC? It doesn't appear to, because you have a wide variety. They seem to be pretty stable over time. I'm just curious why not.
So the disks were thicker at earlier times.
Yes.
That's a generic thing we see.
Okay. Why would that make a difference in the collapse time and the properties of the GMCs that result from the...
Well, we didn't measure the collapse time at high Z. So far we measured the lifetimes at redshift 0. We're in the process of revisiting this at higher redshift. So I don't have, but I can certainly say the ISM itself was much thicker in these progenitor simulations at high Z. That's generic of all of these runs.
Any more questions for Andrew? If not, let's thank him again.